afternoon. My name is Karen Shunk with the Energy Management Association, and I'd like to welcome you to today's webinar and thank ONICON Incorporated for sponsoring today's session. A few items before we get started. Presenters will be holding questions until the end of the presentation, but we encourage you to submit them at any time using the Q&A button at the bottom of the screen. If you happen to be experiencing technical problems during the webinar, please use the Q&A to inform the panelists, and our producer, William, will assist you. This presentation is being recorded and will be available for viewing in 1 week. In terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. And finally, if you are a certified CXA or EMP, your CEUs will be automatically uploaded to your respective portals after the webinar concludes. Today's webinar is optimizing building systems, leveraging flow and energy measurement for efficiency and performance. Our speakers are Zack, Landis, and Francisco Valentine. Zack is a senior regional sales manager at ONICON Incorporated and Air Monitor Corporation. He received his bachelor's degree in mechanical engineering from the University of Florida. Zack began his career in 2011 as a sales application engineer for ONICON Incorporated before moving into a managerial role in 2013. Francisco Valentine, PE, is a BIS engineer at Davisystems, LLC, and is a graduate of West Virginia University School of Mechanical Engineering. Francisco started his career as a mechanical and plumbing design engineer and has expanded his skill set to include energy project development, commissioning, tab, and direct digital controls. Thank you again, everyone, for joining us. And with that, I'll hand it off to our panelists.
All right. Well, thank you so much, Karen. And thank you all for joining us today. We certainly appreciate your time. If you have any questions, please be sure to mouse down to the question and answer section and send us your questions over. We're going to have some time at the end of the presentation to go over them. And so what we're going to cover today, we've got a lot to go over. To start, we're going to cover flow and energy metering basics, how meters are specified and selected. Next, why and how flow and energy meters are used. And lastly, selecting the correct meter for your application and validating its performance in the field.
I like this quote by Lord Kelvin because it's so relevant to this topic. Although we don't realize it, our daily lives revolve around this concept of measurement. We measure time, money, calories, steps, miles, fuel, speed, meal ingredients, etc. Our homes and places of work are protected by smoke detectors, heat detectors, fuses, circuit breakers, all of which alert us to potential dangers, all measured values. Having units of measure give us information that we can use to make informed decisions, control our environment, and provide safety. Okay, in HVAC systems, there are many parameters that need to be measured, controlled, recorded, and alarmed. These include temperature, humidity, current, differential pressure, etc. Plans and specifications are used to communicate flow and energy meter requirements. And I'm going to follow with a few examples. With increasing frequency, we're seeing projects that require flow and energy meters with the impetus on energy efficiency and sustainability. On the left is an example of a mechanical design of a variable volume condenser water system with a flow meter. On the right, we have an air handling unit with a water source heat pump system. An energy meter is shown and clearly indicates the flow meter and the two supply and return temp sensors, which allow us to quantify the energy transfer to and from the condenser water system. Point schedules are another method in which flow and energy meter requirements are communicated. They're typically found in the mechanical plans, but they may also be found in project specifications. This is an example of project specifications that you might see for energy and flow meters. They provide the design requirements that are in addition to what's shown on the mechanical plans. They may have their own specification section, or they may be included within the building automation system spec. We can see from this spec section that an ONICON F3100 electromagnetic flow meter is the basis of design, and that it must be provided with a hardwired as well as backnet communication capability.
So with all these various methods of conveying to us, we need to put meters here. How do you select the right flow meter? There are numerous considerations to make when selecting a flow meter, and we're going to go into detail on that and cover a few of the more common issues in a couple slides. But first, before making this determination, it's really important to understand the basics of flow meters. What are the types of flow meters that are commonly used in this industry, the pros and cons of each technology. And so to break it down a little bit, we're going to start with the basics, the different types of flow metering styles we typically see in HVAC. They usually fall into one of three categories. Insertion meters are typically installed through a ball valve, and this allows you to insert or remove the meter from the pipe while it's up and running without requiring a shutdown. Full bore meters are installed in line with the pipe. So they're typically installed with a flanged or threaded connection. And then lastly, clamp-on meters would be strapped to the exterior of the pipe, typically using an ultrasonic signal to measure the internal flow. And so each of these styles has pros and cons. The insertion style meters are typically the most cost-effective solution because their price remains consistent, even in larger pipe sizes. Another added bonus of this technology is the ability to hot tap the meter into a live and pressurized system without requiring a shutdown. Very popular in retrofit applications. And if you're not familiar with this, we're going to show you a little bit about it on the next slide. But there are drawbacks. With insertion meters, since you're typically only sampling a small portion of the flow passing through the pipe, there are straight run requirements that may need to be considered. So the hot tap process, for those of you unfamiliar, allows for an opening to be created in a pipe wall without any water escaping from the system. So the system can be live and running. And essentially what you do is, weld or use a saddle to attach a ball valve to the pipe. And then you use a wet tap drill to push the drill through the ball valve, penetrate the pipe wall, and create an opening that the meter can be installed to. Retract the drill back out of the pipe, close the valve, and then you're ready to install your flow meter. Insertion style meters typically use one of two metering technologies. Insertion turbine meters are mechanical in nature. They use a rotating turbine assembly, which directly measures the fluid velocity, and then that's used to then calculate volumetric flow rate. These meters offer the best value. They're highly accurate, relatively simple and inexpensive. They can be hot tapped, and they're easily reprogrammable if the field conditions change. But since this technology has moving parts, it limits the applications in which they can be used to systems with relatively clean water. The second technology is insertion electromagnetic. Electromagnetic meters have no moving parts, so they are well suited for open loop cooling towers or closed loop systems with poor water quality. They can also be hot tapped and use the same installation components as the turbine meter. And so this is a really great value product because it brings electromagnetic technology and reliability to even large pipe sizes at a reasonable price. Next, we have full bore meters. Full bore meters are installed in line with the pipe so that the entire flow stream passes through the meter. This meter typically controls the measurement area, which generally results in a more accurate measurement. The drawback to this is that the cost increased with pipe size. And if you ever want to service the meter or install the meter in a retrofit application, it would require either a bypass or a shutdown to get that out of the pipe, into or out of the piping system. Inline meters in our industry are typically electromagnetic meters. And so these meters are highly accurate. They definitely provide the best level of performance in limited straight pipe situations. The primary and really only drawback is the cost associated with purchasing them, installing them, and servicing them. And then lastly, but certainly not least, we have clamp-on style flow meters. Clamp-on meters are strapped to the outside of the pipe. They require no mechanical work to get them installed. There are both permanent and portable versions of these meters available. Portable meters are often used for balancing purposes. And so we work with these meters routinely, even if we're using inline or insertion style meters. We run into these quite often in this industry. Clamp-on meters are typically transit time ultrasonic meters. And so transit time ultrasonic meters are highly accurate, but the performance can be affected by the pipe conditions. So if you have a really old corroded piping system, it can be a challenge to get it installed and operational. These meters are priced independently of pipe size and can be but they can be fairly expensive for smaller lines. And so they're a better value on larger sized pipes.
Most energy and flow meters will be connected to the building automation system. Flow meters may be hardwired between the flow meter and the BAS controller with a pair of wires that provide a current or voltage signal. The analog signal of the meter is then simulated within the controller so that it knows how to interpret that flow signal from the voltage or current signal. Flow meters may also be connected to the BAS through communication wire, namely RS-485 or Ethernet, which are the two typical standards that we use. Once connected, the energy and flow meter data is communicated to the BAS through a communication protocol, typically BACnet or Modbus. When the energy flow data is communicated, it does not have to pass through an intermediate controller. It's as is the case with a hardwired flow meter. Structurally, flow and energy meters are essentially the same. They only differ by the inclusion of temperature sensors, as they are required to calculate the energy flow. For tenant billing purposes, energy meters provide more valuable data than a regular flow meter, and that point is demonstrated in the two calculations to the right. Both calculations are based on hydronic flow of 1000 GPM. However, the top heat transfer calculation has a differential of 10 degrees, whereas the bottom has a differential of only 5 degrees. And as we can see, that the resulting energy transfers are quite different. If these two sub-meter tenants were billed based on flow, they would pay an equal amount. However, if the billing were based on energy transfer, tenant 1 would be paying double that of tenant 2. The building automation systems typically use thermistors for temperature measurement and is perfectly capable of calculating energy flow. However, energy meters are much more accurate, and Zack is going to explain why.
Exactly. So, if you understand that you need a BTU measurement to take place in order to accurately calculate flow, and that the automation system you already have can do it for you, why would you need to use a third-party BTU meter? And so in order to control and manage energy usage in a campus environment, you really need to accurately measure individual building loads. Anyone who's tried to rectify a bunch of building loads added together against a main campus meter can attest to how important it is that all the meters are operating correctly and that they're accurate. Submetering applications require accuracy for a completely different reason. When money's changing hands, people are going to scrutinize the data. They want to know that they're being accurately billed for their usage. Their usage isn't being inflated by an inaccurate meter. So what does this look like in the field? How are we calculating this? Using the energy load equation on the right. So in order to calculate the BTU rate, we measure the flow, we multiply that times the delta T, and the specific heat and density of the fluid. That's often shortened in the field to 500, so flow times delta T times 500. And the traditional approach to solving this looks like the image on the left side of your screen. You would acquire an accurate, wet calibrated, hopefully flow meter, 2 quality temperature sensors, you'd wire them back to the local controller, and the BMS would be doing the math for you. However, the effects of temperature sensor accuracy on the energy calculation are typically underestimated. And believe it or not, delta T accuracy is the leading cause of error in these energy measurements in the HVAC world. So to demonstrate this, we're going to use an example of a 100 ohm platinum class A RTD. We're generally considering these to be good temperature sensors in the field. The convenient thing about these is you can use something called the Callender-Van Dusen equation to calculate the accuracy range for these sensors at any temperature. But the key here is that Class A RTDs and thermistors and everything else that you would normally see in the field isn't calibrated and matched. So the delta T errors can be substantial, even if the absolute measurement error is minimal. And so on this slide, we have a breakdown of the math, right? So we're using an example with our Class A 100 ohm platinum RTD in a chilled water system with a 10-degree delta T. And so here you can see between 45 and 55 degrees where we would expect the system to operate. These sensors are adding roughly 6% error to the energy rate calculation. And these are good temperature sensors. Lower quality RTDs and thermistors, other sensors that aren't calibrated can be considerably worse. And so the solution, as you might have guessed, is to use calibrated temperature sensors. By using temperature sensors that are matched and bath calibrated at the application temperature, that delta T error can be significantly reduced. These sensors have a delta T accuracy of, should be within 0.15 degrees Fahrenheit. And so if you look at that 10-degree delta T chilled water system again, now our error has been reduced from 5 to 6% down to 1.5%. But the real key here is what happens when the delta T drops. I can't tell you how many buildings I've been in where they're billing a tenant who has a 5-degree or less delta T running through their building. And this is where the problem lies. So here you can see on this graph at 10 degrees, the calibrated sensors are 1.5% and the RTDs are 5 to 6% as we discussed. But if you drop that down to 5 degrees, now our calibrated sensors are operating at 3% error and our RTDs are between 10 and 12%. Even further, if you drop the delta T down to 3 degrees, the calibrated sensors have a 5% error versus over roughly 20% error on this RTD calculation. So these errors can really sneak up on you, and they're generally not expected to occur. And so what we propose is to use a system that is single sourced. All of the components are calibrated together, so you can provide an accuracy statement on your energy calculation. And so that configuration would look something like this. You're still providing an accurate flow meter. You're using 2 calibrated and matched temperature sensors now, and those are all wired back to a local BTU meter. And that meter is then performing the energy calculation and is sending that data back to the BMS. And the accuracy on this calculation is better than 2% of rate on the energy calculation. If you compare that to that traditional approach we discussed previously, you're looking at 2% or better versus 5 to 10% error, which may or may not be acceptable, but it is significantly higher. So the key takeaways here, if you want to accurately measure BTUs, you need to provide an accurate flow meter, temp sensors with a published delta T accuracy, and for the best results, single sourced, calibrated at the factory, can be recalibrated as needed, so that and can provide both the tenant and the owner certificates authenticating the accuracy of those products.
Chiller staging of many large central plants with constant volume primary and variable volume secondary flows are largely based on flow rather than temperature. For example, each of these 2,000-ton chillers are equipped with a dedicated primary pump rated for 4,800 GPM, and the secondary pumps are rated at 9,600 GPM. If the secondary flow ever exceeds the primary, then the secondary chilled water return will mix with the secondary primary supply, which we don't want because it will increase the temperature of the secondary supply chilled water supply temp. Flow meters used in conjunction with the BAS help us to automate this chiller staging process, such that when the secondary flow, as indicated through flow meter 5, approaches the primary flow indicated through flow meter 4, an additional chiller and pump are enabled. Now the second chiller and its pump have been enabled, and the primary loop flow is 9,600 GPM. The secondary chilled water flow, as provided by flow meter 5, has exceeded 4,800 and is now on its way to the maximum of 9,600 GPM. As the chilled water flow reduces, the reverse will occur. When the secondary flow approaches 4,800 GPM, the second chiller and pump will be disabled. This is an example of sub-metering. This is a typical energy meter installation in a condenser water system where the energy usage of multiple tenant spaces is sub-metered. Each tenant's energy usage is quantified by a dedicated energy meter to determine their portion of the operating expense of the central. This is a condenser water plant. Ideally, the summation of the tenant energy meters will be equal to that of the central energy meter reading. Minimum flow control is another common application, which is used to ensure safe operation of HVAC equipment, namely chillers and boilers. Going below them risks catastrophic equipment damage and the voiding of equipment warranties. When the downstream cooling coils close off during periods of low cooling load, the chilled water flow can reduce to unsafe levels. A flow meter is used to monitor this chilled water flow, and the bypass valve is modulated open when the flow approaches the minimum flow rate of the chiller or boiler. For safety, the minimum flow set points are usually set 10 to 20% higher than the minimum flow rate. As the flow rate increases, the bypass valve will modulate towards the closed position and will operate normally. Flow meters allow us to detect hydronic system leaks. If the domestic water makeup flow is detected that is outside the normal usage, the isolation valve is closed to eliminate the leakage and minimize or eliminate the collateral water damage. The same strategy can be used to detect excessive domestic water usage in cooling towers and irrigation systems. Some mechanical designs require measurement of cooling tower makeup and blowdown flows. The water level in the basin of a cooling tower is controlled by a level controller or float valve. Water is constantly lost due to evaporation, drift, blowdown, leaks, and overflow. When the level drops, the makeup water valve is opened to maintain the water level. To quantify makeup water usage, a flow meter is installed in the makeup line as indicated. Conductivity controllers are used to control the level of suspended solids in cooling tower basins. Conductivity is an indicator of the concentration of suspended solids. If the concentration gets too high, scaling of the pipes and heat exchanger surfaces will occur, and this reduces heat transfer efficiency. When the conductivity of the condenser water reaches set point, the conductivity controller opens the blowdown valve to drain some of the basin water. At the same time, that water is made up by the feed water valve, and the fresh domestic water dilutes and lowers the concentration of the solids in the basin water. Flow meters allow us to quantify the amount of cooling tower blowdown and makeup water flows. In other projects, domestic water flow is required to be metered. Most commercial domestic hot water systems will include a domestic hot water recirculation loop and circulation pump. During periods of low or no domestic water usage, the aquastat enables the circ pump to keep the domestic water loop hot so that domestic hot water is readily available. When hot water faucets are opened, the domestic water flow begins, and the cold makeup water flow as well is initiated to replenish the tank. And that is why we have the flow meter on the cold water makeup line instead of the hot water supply line. If the flow meter was located on the supply line, it would measure the domestic water usage as well as the recirculation flow, which we generally don't want.
So as I mentioned earlier, there are a ton of different considerations to make when selecting the right flow meter for your application. And so I'd like to narrow this down and only focus on the two that most commonly affect which product is selected. The first question I always ask when this topic comes to mind is, how accurate does your flow meter really need to be? And so we've broken this down into three general categories. The first is cost allocation and billing. These meters require the highest levels of accuracy, and the data is continuously scrutinized. We often provide inline meters for these applications. System control applications require meters that are both accurate and repeatable. In control systems, you need the meter to do the same thing, given the same conditions every time, so that you can, accurately control your system. And then lastly, you have system monitoring applications, and these may have much less stringent requirements and open up, a wide variety of products that can be used. But to understand meter accuracy, you first need to understand how flow meter accuracy statements are built. A valid accuracy statement should include three components: the uncertainty, the reference, and the range. The uncertainty is what we're used to seeing. It's typically a percentage, 1 or 2% is typical. The reference, believe it or not, is the most critical element to this whole thing, differentiates between a percentage of instantaneous reading and a percentage of full-scale error. And the velocity range over which the accuracy is specified. Many flow meters have different accuracy levels based on flow rate. Measuring lower flow velocities harder typically than measuring higher flow velocities. So you need to be aware of how accurate the meter you're looking at is going to perform at the flow rates your application is going to operate. Unfortunately, many percent of full-scale devices leave the reference portion of this statement off of their documentation. So beware of products with incomplete accuracy statements. To illustrate the severity of this issue, I've included a graph on this slide here. And so what we've done is chart the performance of a 1% of rate turbine meter versus a 1% of full-scale device. And so as you can see, our turbine meter has a variable accuracy statement based on the velocity and calibration point of the product. We're interested in this 1% of reading from 3 to 30 feet per second portion. And so you can see this is indicated by the straight line, across the expected flow value. And so with this product, you're always going to be within 1% of at the actual reading in the HVAC flow range of 4 to 8 feet per second. Compared to the 1% of full-scale device, which is the red line here, you can see down at 30 feet per second, the device does indeed provide 1% accuracy as advertised. However, as your flow rate drops, this accuracy diverges. And so in the real world, once you're in that 4 to 8 feet per second velocity range, this device is going to be operating between 5 and 10%. So significantly worse error than you would expect if you were just looking at the catalog sheet and saw 1% listed. Meter accuracy is ultimately dependent on calibration. The way meters are calibrated matters, and wet calibrated meters typically provide the most or are the most accurate option. And so this means that the meter has been not only tested to be functional, but they put it in a pipe that matches the pipe size that your application has, and then run it at the flow rate that is expected for your application to verify that it is performing as advertised. After calibration, the biggest impact that we see is installation. It has the biggest impact on real-world performance. Every meter has its own set of published rate run requirements which need to be met in order to meet the published accuracy. But this is not necessarily a pass-fail binary issue. Trade-offs can be made between the amount of straight run you have and the accuracy required of your meter. And so as a general rule, we like to avoid installations directly downstream of things like control valves, inflowing tees, outflowing tees, or inflowing tees, pump headers, really complex obstructions, very difficult to manage. Next, we have workable conditions, outflowing tees, single bends, pipe size reductions. Those are much easier to work with. And so, we want to select the location based on the upstream obstruction. And this is challenging because it means the longest segment of pipe might not be the best location for the meter. I would encourage you, if you ever run into a situation where you need to get a product that's going to work well, doesn't meet the recommended straight run requirements, reach out to the factory. They should be able to give you an estimate of how the meter will perform, or make a recommendation after reviewing your drawings for an alternate location.
Okay, so now we're out in the field during commissioning or startup, and the flow and energy meter are not providing believable data. What do we do? At this point, the first thing we would do is read the manual. And the manual's full of commissioning, installation, and troubleshooting guides. Next, we would verify that the BTU meter panel, specifically the System 10, D100, or System 1000 panels, are configured properly. In our projects, Zach mentioned matched temp sensors, and what have found through experience is that they don't, when he says matched, that means that sensor 1 has been bath tested and calibrated, and the scale and offsets for each sensor have been determined. So once you have those individual sensor parameters, scale and offset, you have to enter them or connect them to the right point. So if you have a supply temp, you'd want to connect that sensor, given its ID number, to the supply temp sensor terminals of the BTU meter, because they've been matched at the factory. Recently, we had a project where all the flow meters were installed, all of the temp sensors were put in a box, and then the temp sensor thermal wells were installed later. So we just installed temp sensors and we got incorrect temp readings, and we had to go back and match them one for one, which was the supply, which was the return, to get all of the BTU readings and temp readings correct. So make sure that each meter and associated temp sensors remain together, or you'll get some incorrect readings. You'd verify the wiring of the BTU flow meter. You verify that the system was postured and locked in the required operating mode so that the flows aren't modulating. Occasionally we'll do temp sensor set point changes, but occasionally the space will actually reach that space temp set point and then begin to modulate. So it's better from the field perspective just to override the dampers or valves to 100% open rather than do temperature set point changes. You'd verify the configuration of the building automation analog input. There again, we go back to the 4 to 20 milliamp signal as flow goes from 0 to 350 GPM. You want to make sure that that's in there. Verify all your field measurements and calculations, and run it again. You verify proper replacement of the flow meter and its temp sensors, and ensure that the thermal paste has been applied to all the thermal wells. Here's an example of a hardwired flow meter, and this is the analog input. On the right is the analog input configuration, and you can see I kind of gave you a preview, 4 to 20 as the flow goes from 0 to 350. All of ONICON's flow meters come with a nice laminated tag that provides these performance parameters. So you can, if you configure your analog input with exactly the same numbers, you'll get accurate data. When the energy or flow meter is integrated, you just get the final flow value. There is no input configuration to change. Okay, so we have, now we're getting field flow data, and we want to validate those readings. These are the 4 most commonly used methods, and they include the heat exchanger differential pressure method, the triple duty valve method, pump curve method, and the use of the ultrasonic flow meter. So this is a plate and frame heat exchanger performance sheet. And the most important pieces of data to note are the flow versus pressure drop. So most heat exchangers will have a similar performance sheet. So if we wanted to validate the flow meter reading, we would take a differential pressure across this heat exchanger and then use the pump laws to calculate the flow at the alternate DP. And as we can see here, we have a flow of at a flow of 1,080 GPM, the pressure drop through that heat exchanger is 6.41. But if we were in the field and we happened to measure 6.74, this is how we would calculate that flow and then use this value to compare against what the flow meter read. Okay, pumps typically have a triple duty valve on its discharge, and it's called a triple duty because it serves three purposes. It's a check valve, it's a balancing valve, and it's an isolation valve. Okay, if we take differential pressure across the valve, triple duty valve taps, we'd get a DP, and then having the performance curve for this triple duty valve and knowing its valve position. In this case, it's fully open, and we measure 6.75 feet of head. And then we draw a line horizontally to the appropriate curve and then go down to the horizontal axis, which gives us the flow. And then we can use that value to compare against the flow meter reading. We can do the same thing with a pump curve, but the first thing we would do before comparing or measuring any DPs is to verify what the impeller diameter is with a no-flow test. So in this case, we've verified that it's a 9-inch diameter impeller, and then we can take our DP read in the field, which in this case is 50 foot of head, draw a horizontal line over to the 9-inch impeller curve, and then go down to the horizontal GPM or flow axis, and then we'd read that we had a 825 GPM, and then we can then compare that to the flow meter reading. Okay, now this method is just using a conventional ultrasonic flow meter. It's a non-invasive method of acquiring the flow rate directly. Pipe surface is a key to acquiring flow readings. Occasionally, internal corrosion, linings, and sediment can make acquisition of readings impossible, but in most cases it works. And this is a great system for older chilled water and hot water systems where there's very little to no documentation. Sometimes nameplates of pumps are removed. You can't determine what balancing valve is installed. And when you can just install this meter on the pipe and acquire a flow, it's perfect. The only caveat is that I would bring an ultrasonic thickness gauge with you because in some areas, especially outside the US, what you would assume normally is Schedule 40 pipe is a lot of times not that at all, and that can make a big impact on the resulting flow reading.
All right. And so, one thing I'd like to note here is that a flow meter with 1% of rate accuracy is significantly more accurate than the calculations performed using these verification methods. Even portable clamp-on meters are typically around 1%, and that's, on the higher end side of things. So if a wet calibrated flow meter is off by more than a few percent versus your calculation, we need to find out why. Most discrepancies are installation related. And so I can't tell you how many times I've gotten a call, from someone in the field saying, hey, your super expensive 0.2% of rate inline mag meters off by 10%, according to, my tests. How do I reprogram it? And so I'd like to encourage you to pause and investigate why this is happening. ASHRAE standards call for a calibrating meter to be 5 to 10 times as accurate as the meter that it's being calibrated. And so wet calibrated instruments shouldn't really have their outputs adjusted unless there's a, reasonable explanation for the discrepancy. I've got no straight run, but I'm just trying to get a reading. Let me match the balancer's reading with this meter, and we'll do the field rescale. But we want to explore that first. We don't want to jump the gun and change these parameters in calibrated meters without a justification. And so to wrap this up, I want to touch on some of the added benefits, to using accurate flow and energy meters. And increased efficiency is a big one. More accurate metering allows for finer control, which obviously increases the efficiency and reduces the cost of operating the entire system. And it provides data for informed decision-making. And so whether you want to reduce cost, identify potential maintenance issues, or plan for future expansion, all of those decisions require accurate data. And lastly, but certainly not least, tenant billing. Energy usage is financially incentivizing them to conserve, or accurate billing is financially incentivizing tenants to conserve energy. When we're billing by square footage, I've seen some wild scenarios where you've got a shopping center with the doors wide open in the winter, blasting heat out onto the street up north, trying to entice customers into the building when it's really cold. If you're billing that tenant on square footage and everyone else has to pay the difference, it's pretty painful for everyone. So with that, we're going to wrap it up, and I would ask you for your questions. So if you have any questions, please, there's a Q&A box at the bottom that you can type them in, send them over, and we'll be happy to answer them for you.
Well, thanks, Zach and Francisco. Very interesting presentation. And I always exercise my prerogative as the moderator, ask a few of my own questions first. So, so my first question is, I'm thinking of a few situations I know of, like, for example, here in DC, where one university took over another university and actually took over management of that new of all their facilities and that kind of stuff. And of course, there was a little bit of deferred maintenance, et cetera. I'm also thinking of people I know who've taken over buildings that were then subsequently completely renovated, and so they had no baseline. And I'm just wondering where to get started. So in the instance of an old building you take over and there's no metering at all, I mean, how would you recommend that people get started? What's the, kind of the process, the thought process?
Well, right. And so, the first step is gathering data. And in our experience, we've had many campus environments, universities, hospitals reach out to us and say, hey, we've got meters on our mains. We know what the plant's producing, but we don't know anything else. And so typically the first point is put a meter on each building. And you just have to measure hot and cold water. Once you know the energy going in and out of each building, you can then start exploring, why is building A using twice as much energy as building B? And does it make sense for us to sub-meter further? So the real key is data. The more information that you can gather, the better off you'll be in solving whatever problem you're trying to resolve.
Okay. Francisco, did you want to add anything to that? I wasn't sure if you were.
No, he's covered it pretty well.
Okay. Okay. Well, we do have some other questions, so I guess I'll defer to those. We have Jeffrey asking, how does the hot tap EM sensor compare in accuracy and cost to the turbine sensor?
Both meters provide 1% of rate accuracy. They're both wet calibrated. The cost, it is more expensive. And so, it's not, you're not spending $10,000, but it is more expensive than the turbine meter. As a general rule, I like to say turbine meters are around, say $1,200, and an insertion mag meter would be around 2,000, maybe double.
But no, I'm sorry, go ahead.
Sorry, another consideration would be that the electromagnetic flow meter has no moving parts. So I learned many of my lessons the hard way. And I was in Honduras validating a flow meter reading, and it was a turbine for a chiller. So I used that differential pressure method. So I took a DP across the chiller barrel, used the flow versus DP reading to calculate the flow. And we found that we were more than 50% off. So we checked everything over, checked all the settings, and we said, well, we can't find any reason visible that, why we would be more than 50% off. So we removed the flow meter and found that Teflon tape strands had wrapped around the axles of the turbines and the blades themselves. It was just, it had many strands of Teflon tape, which slowed its rotation and provided a low flow reading. So, we cleaned it up, removed all the Teflon tape, made it nice and pretty again, installed it, and then we were within 5% of flow again. So at that point, I became a big fan of the electromagnetic, because there are no blades for any Teflon tape or any other material in the pipeline to wrap around.
It was so excellent. You covered my follow-up question.
You're welcome.
Right on. Okay, so we have a question from Joel. What's best if you are limited in straight pipe run without obstructions for flow meter?
Yeah, unfortunately, that's the most common issue that we run into. Mechanical rooms are getting smaller and smaller. And the first question I like to ask is, can we review the drawings and see if we can find a good location? Because the convenient place to put the meter, there might not be straight pipe, but somewhere else in the loop, there might be a location where you can capture everything we need. Outside of that, unfortunately, is spend more money on your flow meter, buy an inline meter. To give you some comparison, insertion meters typically require about 15 diameters of straight pipe. Inline meters only require 5, and that's measured from the middle of the body. So on smaller sizes, or 2 or 3 inch line, the body itself makes up most of the straight run requirement. We've also tested inline mag meters to provide better than 1% of rate accuracy when installed with 0 straight run directly between 2 elbows. And so, even if you don't meet the requirements there, unless you have a very, very challenging piping configuration upstream, those meters are still going to give you a very accurate output.
So we just have a real quick follow-up question from Jeffrey. You'd asked about the turbine meters, and he says, what's the typical life expectancy, of a turbine meter?
So it's very, very system dependent. When I first started at ONICON, it was 2011. We had a turbine meter returned that was 22 years old. And we did a as-received calibration verification on it, and it was within 1% of the original calibration, which blew my mind. Come to find out, it was at a IBM data center, honestly, and they were using the water to liquid cool computer chips. So it was very, very well maintained water. It was very clean. So the turbine meter lasted forever. We use neutrally buoyant turbines. The shaft is tungsten carbide. The bearings are sapphire. So very robust components with, very light turbines mean in a clean water system, it's going to accurately last for a very, very, very long time. But, on the flip side, when I was young, I assumed closed loop meant clean. And then my first time out on a college campus, looking at their system, they opened a tap, and when the water came out, I was shocked at what it looked like. And so, over the years, I've learned that closed loop definitely doesn't imply cleaned. It means, that the system's not open to the atmosphere, which does eliminate a lot of problems. But like Francisco said, Teflon tape, #1 killer of turbine. No joke. The convenient thing is you can take it out and clean it, and it'll go back in and keep working. But no one wants to do that, and so it can be a challenge in those systems with low quality water.
Well, here's a question that is kind of parallel, kind of in line with that. It says, what's the expected lifetime of a solid state sensor, and how often do they need to be calibrated given the drift in semiconductors?
Over 10 years is what we've seen. We see very few temperature sensor failures. Recalibration intervals is an interesting topic in general because America doesn't have a billing standard for meters. There's nothing that we can point to through ASHRAE or anything that's accepted on a national level. It says, hey, if you're billing a customer, here's how often you need to recalibrate your meter, or even what your meter accuracy should be. It's all left up to the owner tenant discretion. And so we get asked for the flow meter side as well. How often do I recalibrate my flow meter for a billing application? And it really varies by the technology, the type of meter, all of it plays in. So, if you had an inline mag meter, you probably never need to recalibrate it. If you have an insertion meter and you're billing someone $10,000 a month for their energy usage, maybe get it recalibrated every year. The meter itself probably doesn't need it, but the tenant might need it for peace of mind. And the same can be said with temperature sensors, is that, if you're just monitoring your system over a 10-year period, we expect very minimal drift to happen. But if you're billing someone, maybe they need to know that that sensor has been calibrated every couple of years, or you could even have spares on hand. And so swap in inexpensive calibrated sensors to your meter, send the ones that were in back to us for recalibration. And that way you never have any downtime and you always have an accurate temperature measurement. Our sensors, as Francisco mentioned, are provided with slope and offset calibration parameters. And so in your BTU meter, you get new temp sensors, you can just reprogram those two variables and you're not losing any accuracy. And it's very simple to move from one sensor to the other.
Okay. Here's a comment and then a question from Chuck. He says, I shuddered when you mentioned triple duty valves. Great points on measuring pressure drops on equipment to assist in determining flows, but isn't this dependent on where the measuring ports are located on the equipment being tested?
Definitely. Yep. Especially when the tap is like beyond the suction strainer. It has to be right at the inlet and outlet of the pump and at the inlet and outlet of the heat exchanger. Like if you include any more pipe, that the curve is not meant to encompass additional piping components. It's just of the chiller barrel, it's just of the pump, and it's just of the triple duty valve. So if your tap is somewhere else, that's going to impart additional air into your flow calculation.
Okay. We have a question from Mohammed. He said, BTU metering can be a smart city use case. What is a good source of information on the various options to connect a large number of BTU meters to a smart city platform? There could be more than one option for the communication system infrastructure, LoRaWAN, 4G, etc., and the cost varies. So the question, so let me just say again, the question is, what is a good source of information on the various options to connect a large number of BTU meters to a smart city platform?
Yeah, I mean, we've found that our meters, most people are interested in BACnet these days. And so there are many controllers that will bring data up to the cloud that can convert, an HVAC communication protocol to an IoT, cloud data communication. And so there's really a lot of options. Francisco, do you have any experience there?
No, that's a lot bigger than I deal with. I'm usually building by building. A campus, that's pretty big talk for me.
So I would imagine that IP types of communications, BACnet IP, Modbus TCP/IP, those types of protocols would probably pretty seamlessly integrate into those controllers that allow for cloud connectivity. It allowed them to take individual points, from BACnet up to the cloud. And so I would imagine some sort of third-party signal converter would need to be used to bring all that data online. That's not something that I've had personal experience with.
So I have a question here. What do you do? So this is a troubleshooting question. What do you do if you've tried all of your troubleshooting steps and the installed flow meter and the balancers don't agree?
So the first thing I like to tell all my customers is if you're looking at a flow meter, getting frustrated, spending more than 5 minutes on it, please call us. We've got a staffed team of engineers ready to help you with troubleshooting, tech support. They'll step you through the process of, evaluating how the meter is configured, evaluating how the meter is installed, and then providing guidance from there. We get into that situation pretty frequently where, the test and balance guy's got to be within X% and we're not there. So we need to make some adjustments somewhere. And sometimes that's okay. But the question is that we want to resolve is, why is this happening? I've seen it where someone's using a pump curve and it turns out they're using the wrong size impeller pump on their graph. and come to the wrong flow rate. And I've also seen it where that was actually correct and our meters installed in, a situation where there's no straight run. And so if you know, I have very limited straight run, the balancer has probably got a pretty good feel for what's happening in the system. Maybe at that point you do make an adjustment to the meter. But we would want to do sort of a root cause analysis of the situation before we jump in and start reprogramming things. Because at that point, we can no longer guarantee the accuracy of the meter.
Okay. You got anything on that, Francisco?
No. I was going to mention, I'm a controls guy now. So I used to be a commissioning guy. So I was with a commissioning agent, and the flow was correct. I had an issue with the temperature sensors. So as I mentioned earlier, this was a project where all the flow meters were installed. The temp sensors were installed later. So all the temp sensors for all the flow meters were in a box. So they just got installed here, one got installed there, because we were thinking they were just all the same. But when, as Zach mentioned earlier, matched temp sensors. So the supply and return have been calibrated, and those flow coefficients or scale and offset have been programmed in the BTU meter. So they're looking for a particular temp sensor to be connected to them to provide that accurate flow and BTU calculation. And then when they get a random temp sensors that's not the one that's programmed, you will get temp readings that are off. So I was in a central plant. I'm getting the same temperature on the supply and return, therefore no BTUs are being calculated. And I said, uh-oh, commissioning guy's coming today. I got to figure this out. So I went into the settings, found the scale and offset for the return temp sensor, and bumped it up 5-6 degrees. And then later checked it with a balancer. But still, we had to locate the temp sensors, the correct temp sensors, and then get them installed so that we were providing the correct data. But that was just a quick fix with the commissioning agent on the way. So
it must have made you feel great.
Well, I got something believable, because the RTUs were calculating 250,000 BTU, and I had 4 of them. So you're looking for roughly 1 million. My plant was putting out like 40,000 BTU. And I was like, this does not look right. And if he adds things up, he's going to find that this is not right. So I kind of made it right temporarily until I could make it right for real.
Oh boy. Okay, so we have time for one last question. I know, Zach, you answered this in the context of, tenant, easing their mind when it comes to billing accuracy. But otherwise, how often do you think flow meters should be recalibrated, just operationally, for operational purposes?
Yeah, sure. So, billing is like you said, totally different beast. For control applications, certainly not once a year. We usually recommend our customers to, if you're actively monitoring your data, if you see a divergence, send the meter back and recalibrate it. There's not typically a need to recalibrate a meter that you expect is working accurately, especially if the meter doesn't have moving parts. But if it is a critical application and you need to know that the meter is accurate, you could send it back every few years. But really, at that point, you need to consider having a validation routines, in your, how do you want to ensure that your system's maintaining its accuracy? Are other products in the system being recalibrated on a set interval? Should maybe consider having a spare meter on hand, so that, swap them out. If the reading's the same, you can be confident that it's still accurate. And if they're not, you can send that meter you just removed back for recalibration. And the next time you're ready to pull one out, try again. And, so unfortunately, the answer is kind of wishy-washy. It varies. It depends.
Okay. All right. Well, thanks again, gentlemen. This has been a great webinar. Lots of great information. I just want to let everybody know, Zach, if you want to flip over to that last slide, make sure everybody knows that we're doing an Energy Management Professional EMP seminar, November 6th through 7th. So if you're interested in the EMP, that's a commissioning-based energy management certification. That'll be taught by Robert Knadler. So thank you again, Zach and Francisco, and thanks very much to ONICON for being our sponsor. Thank you.
Thank you.